Hello everyone. In this lecture, we're going to talk about three-dimensional vectors. So far we talked about Cartesian plane, we talked about two-dimensional plane, we talked about points on the plane with two coordinates, x coordinate, y coordinate. We talked about two-dimensional vectors, Cartesian vectors, algebraic vectors. Now we want to go 3D, three-dimensional. So instead of having only x and y axis, we have a third axis, which is the z axis here. And that point O, the origin, is the same as what it was before. So instead of cutting the plane into four quadrants, as we have always done that, quadrant 1, 2, 3, 4, by drawing two perpendicular axes, which is the x-axis and y-axis. Now this time, we are using a third axis and we are dividing the space, actually, the space of this room into different octants, we call them, not quadrants. So if we have like x-axis, y-axis, and z-axis, that they extend from negative infinity to positive infinity, each one of them, then in that case, we are basically dividing the whole space around us into basically 8 octants. This octant here in front is like octant number 1, and then there's one behind it, and then there's one behind it to the left, and then there's one on the left hand side. So that is like sort of 4 small rooms in a building on the second floor. If you can imagine, this could be your classroom, and these are the rooms, adjacent rooms, room 253 to room 254. And below that, in the first floor, we have like other 4 rooms just underneath those classrooms on the second floor. So we have like 4 octants at the bottom, 4 octants at the top, and each one of these spaces that are divided by these axes and by these perpendicular planes is called octants, actually. OC TANT. So in a plane we had quadrants. Now in the space we have octants. And the origin is where the 3 axes meet one another. We have x-axis, y-axis, and z-axis. And in order to label these axes, we always use the right-hand rule. And the right-hand rule says that if you hold your hand like this, so that the 4 fingers point at x-axis positive direction, okay, then when you bend your 4 fingers, they bend towards what? They bend towards the y-axis, right? Okay, if that is the case, then automatically the direction of the thumb, which is pointing up, would be the direction of z, okay? So that's how we name them. Like you can't name this axis like y-axis, that one x, or like change the order. You may change the order, but that's not the standard that we always follow, okay? We always follow a standard system of coordinates in 3D. So if you have a point, obviously, other than having x coordinate, y coordinate, it's going to have a z coordinate as well. So let's plot a point with coordinates of, let's say, 4, 3, and 5. Okay, so 4 is the x coordinate, and the y coordinate is 3. So that will be here. So that's 3 there, that's 4 here. And the z coordinate is 5. This is 5. So if I go up like this, that's 5. I can draw a line parallel. And there you go. That would be the point with that coordinate. And you can actually draw a box here. And you will see that we will end up with a rectangular prism after we draw all these parallel lines, sorry. So this is the rectangular box I came up with. And this point at the corner, which is in front of you, is actually point A with coordinates of 4, 3, 5. Okay? And if you join the origin to this point A, you end up with a position vector. So this is vector OA, which is the position vector of point A in 3D. Okay, and the coordinates of point A is right there. Now, if I want to write the vector, position vector of point A, it's going to be 4, 3, 5, but I use square brackets, obviously. Okay, that's the position vector. So that is a three-dimensional vector right there. Okay. Generally speaking, you may have any 2 points in any part of the space. So 1 point here, 1 point there. Okay, so if you connect these two, like right now, this is like a vector here. Okay, 1 point is here, 1 point is there. Both points are three-dimensional, and we want to find the magnitude of this vector, for example. The formula would be the following. So if you have point A with coordinates of x1, y1, z1, and point B with coordinates of x2, y2, z2, then vector AB would have a magnitude of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. So that will be the formula that you can use to find the magnitude of a vector. Right now, this vector OA has a magnitude, which I would say it is 4 minus 0 squared plus 3 minus 0 squared and 5 minus 0 squared. Okay, so that's 16, 9, 25. So that's square root of 50 or 5 root 2. So that's the exact value of the magnitude of vector OA. 5 root 2 is the magnitude of this vector. So in 3D, that's the formula we use to find the magnitude of any three-dimensional vector in the space. The dot product formula is the same thing that we have in two-dimensional. It's just expanded right now. So if you have like two vectors, vector U, U1, U2, U3 are the components. So X component, Y component, Z component, and vector V with components of V1, V2, V3, then U dot V becomes U1, V1, okay, plus U2, V2. This is the formula for the 2D we had before, and now plus U3, V3, of course, okay? So that last part we added. That's the formula for dot product of two vectors in 3D. And of course, that other formula is still valid. Magnitude of U times magnitude of V times cosine of the angle in between. And these two vectors U and V can be, of course, three-dimensional. That's not an issue. All the properties we discussed are the same. I mean, commutative property for the dot product, associative property, distributive property, all of those properties are remaining the same for three-dimensional, and nothing changes. Unit vectors, we have 3 axes instead of 2 axes now, so we're going to have 3 unit vectors along 3 axes instead of the former I hat, j hat, 2 unit vectors along x and y axis. So now we have this scenario here. We have I hat, no, this is I hat, this is j hat. Now we have a third one, which is denoted as k hat. Okay, so I hat is the unit vector along the x-axis, j hat unit vector along the y-axis, and the z hat is the unit vector along the, k hat is the unit vector along the z-axis. And these vectors can be written as 1, 0, 0 in three-dimensional form. Right now, they are unit vectors end of the day. J hat would be 0, 1, 0, and k hat would be 0, 0, 1. Okay, these are the algebraic form or Cartesian form of the unit vectors along the three axis x, y, z. And the operations with the vectors is almost the same as what we had in 2D, except that we have a third component. Like when you want to add two vectors, you add the components. In the past, we used to add the x components and y components. Now, we just have to add the z components as well. Or when you're subtracting two vectors, you just do the same thing you did before. You also subtract the third components or the z components as well. So everything is as it was before. Let's say we have a vector u with components of 2, 0, negative 4, and 1, 5, 10. Okay, so we want to calculate 3 times vector u minus 1/5 of vector v, let's say. So this would be 3 times 2 comma 0 negative 4 minus 1/5 of 1 comma 5, 10. So that would be 6, 0, negative 12. And then this would be 1/5. That would be 1 and 2. So 6 minus 1/5. That is 29/5. Is that right? And 0 minus 1 is negative 1. And negative 12 minus 2 is negative 14. So there you go. That is the answer to 3 times vector u minus 1/5 of vector v, given the two vectors u and v like there above. That's the answer. So operations with vectors in 3D is almost the same as what we had in 2D, except that we add one more component to our calculations. For now, I think I mentioned almost everything. You can practice drawing these rectangular prisms and practice drawing different vectors with different coordinates of points. You can use graph paper if you want. Yeah, for now, this much I would say. Okay, keep practicing, and I'll talk about more examples later. Thank you.